Are you ready for this? This year's Nobel Prize in Physics is causing some serious head-scratching.
Yeah, it's definitely got people talking.
It's for work in neural networks. Neural networks.
Which, usually we think of as like computer science, right?
Exactly. And that's why everyone's asking, why is the physics prize going to something that seems like AI?
It is a bit of a head-scratcher at first.
So that's exactly what we're diving into today. We're going to be looking at the work of John Hopfield,
A physicist,
and Geoffrey Hinton, who's a computer scientist.
to kind of see how their research ended up blurring the lines between these two fields.
And it really highlights how knowledge doesn't always fit into neat little boxes, right?
Exactly. It's all interconnected.
Okay, so let's get right to it. Why is the physics prize going to something that feels like computer science?
Well, I think it's important to remember that computer science is actually behind a lot of scientific breakthroughs these days, even if it doesn't always get all the attention.
Right.
Like, remember AlphaFold, that AI that predicted protein structures.
Won the Chemistry Nobel Prize.
Snagged the Chemistry Nobel a couple years back.
Yeah.
That's a perfect example
That's wild.
of how algorithms and computation are really changing how we do science these days.
Okay, that makes sense. But how does physics, like actual physics, relate to AI? It feels like we're talking about two totally different things.
Maybe not so different.
Really?
Remember that quote from the computer file video? One of the researchers said, I think it's nice that we're sharing the wealth a little bit.
Oh, yeah, I remember that.
It really kind of sums up the whole collaborative thing here, right?
Yeah.
And to get the connection to physics, let's look at a model that physicists use to understand how things work on a really, really basic level. It's called the Ising model.
Okay, break that down for me. What's the Ising model all about?
Okay, so picture like a simple board game,
Sorry.
like a checkerboard, but instead of checkers,
Okay.
each square has a tiny magnet.
Huh.
And this magnet can point either up or down. So think of it like black for spin up and white for spin down.
Okay.
And the rule of the game, each magnet wants to be like its neighbors.
Hmm.
And that's it. That's the essence of the Ising model.
Okay.
It's just a simplified way to describe how these tiny magnets, or electron spins, interact to create larger scale magnetic behavior.
So even though it's super simplified, it still gets to the core of how magnetism works.
Exactly.
Wow.
It strips away the complexity so we can see what's really going on underneath.
So is this where Hopfield comes in?
You got it.
Okay.
Hopfield was like, hey, physicists use simplified models to understand complex stuff. Maybe I can do the same thing to figure out how memory works. And he created something called a Hopfield network,
Okay.
which is basically a simplified model of the brain.
Interesting.
So instead of magnets that are up or down,
Yeah.
you've got neurons that are on or off, and they represent bits of information.
Like a 1 or 0.
Or like ones and zeros, yeah.
I'm starting to see how this connects. But how does a network actually remember something?
So remember how in the Ising model, those little magnets want to be like their neighbors?
Yeah.
Well, the neurons in a Hopfield network are connected,
Okay.
but by weights that determine how much they influence each other.
Okay.
Think of the weights like the rules of the network. And these rules dictate how the neurons want to arrange themselves. So you train the network by adjusting these weights to store certain patterns.
Oh, I see. Like a specific image or something.
Yeah, exactly. Or a
Yeah.
sequence of numbers.
Cool.
Like you're setting up the board game so the pieces want to make a specific pattern.
Yeah, I get it.
And once the network is trained, it can retrieve those patterns even if the input is a bit messy
Oh, interesting.
or incomplete.
So it's like recognizing a song even if there's some noise in the background?
Yeah, exactly. Or, like you said earlier, identifying a smiley face, even if it's distorted. That's associative memory in action.
This is amazing. So Hopfield used physics to understand how memory works. Yeah. But what about Hinton? He's part of this story too, right?
Yes. And this is where things get even more interesting.
Okay.
So Hinton took Hopfield's work and ran with it. He developed something called Boltzmann machines.
Okay, what are Boltzmann machines? And how do they change things?
Boltzmann machines are neural networks too, but they're kind of special.
How so?
They can learn from data without being specifically told what to do.
Wait, so you're telling me this algorithm just learns, like, on its own?
Pretty amazing, right?
Yeah. How does that even work?
Instead of being programmed with all these rules, the Boltzmann machine just figures things out by adjusting those connections between neurons, like the weights we talked about, based on the patterns it sees in the data.
So it's like figuring out a puzzle without even knowing what the final picture is.
Yeah, kind of like that.
That's incredible. So Hinton is the one behind this.
He was super important in developing this idea of unsupervised learning, and his work on Boltzmann machines,
Okay.
it really had a huge impact on the whole AI field.
Wow.
And it led to something called backpropagation,
Propagate.
which is like the main algorithm for training almost all modern neural networks.
Okay, you're going to have to explain that one. What
Yeah.
is backpropagation and why is it so important?
Imagine you're learning to play basketball,
Okay.
and you keep missing your shots,
Yeah.
and you realize, oh, I'm releasing the ball too early.
Hmm.
So you adjust your technique.
Right.
Backpropagation is kind of like that, but for a neural network.
So it's like the network is learning from its mistakes.
Exactly. It's an algorithm that lets the network adjust those connections between neurons.
The weights.
The weights, yeah, based on how far off its predictions are from the real deal.
So the more the network practices, the better it gets.
Exactly. And that's why we can now train these super powerful AI systems
Yeah.
that can do things like recognize faces in a crowd,
That's crazy.
translate languages on the fly, and even predict protein structures like AlphaFold.
That's right. So this Nobel Prize, it's not just about Hopfield and Hinton, right?
Right.
It's about all these amazing ideas and how they evolved
It's a whole journey.
from magnets to AI.
Yeah. It really highlights the importance of that fundamental research and
Yeah.
how those super abstract ideas can lead to real-world breakthroughs.
Yeah, but there's been some discussion about whether this prize is really a physics prize, hasn't there?
Yeah, there has.
What are your thoughts on that?
I think the debate itself is really interesting because it shows how sometimes our categories for knowledge can be a bit limiting.
Right, because these days science is all about different fields working together. Right.
Exactly. Discoveries often happen at the intersection of like completely different fields.
It's true. And remember the title of Hopfield's paper.
Neural networks and physical systems.
It's like he was already trying to connect those two worlds way back then.
Totally. And this prize celebrates that whole spirit of collaboration.
Working across disciplines.
Exactly.
And it makes you think, what could we achieve if we break down even more of those walls between fields?
Yeah, imagine the possibilities. This could lead to some crazy advances.
Like what?
In neuroscience, materials science.
Hmm.
Imagine designing new materials with AI
Wow.
by simulating how atoms interact.
Or using AI to understand how the brain works.
Yeah. Think of the new treatments we could develop for neurological diseases.
It feels like we're entering this whole new era of scientific discovery,
It is a really exciting time.
where anything is possible.
This prize is like a reminder to stay curious,
Yeah.
to question everything.
To keep exploring how it's all connected.
Who knows what we'll uncover when we dare to think outside the box.
This deep dive has been incredible. We've gone from simple models of magnets,
To the incredible power of AI.
and it all shows how seemingly unrelated fields can come together.
To create something truly remarkable.
And it all started with that fundamental question.
How do things work?
A question that has driven science for centuries.
And still inspires us today.
It's so true. This 2024 Nobel Prize in Physics shows us that the search for knowledge has no limits.
We can achieve anything when we push those boundaries.
And embrace the unexpected.
Exactly.
So until next time, keep those minds open and never stop exploring. It really makes you wonder what's next.
What we might discover.
If we keep pushing those boundaries.
Yeah, what amazing breakthroughs are just around the corner.
It's exciting to think about.
It really is.
This has been such a cool journey.
I know, right? From those simple magnet models
To AI.
to AI. It's mind-blowing.
It really shows you how totally different fields
Can come together.
to create something truly amazing.
It's a testament to human ingenuity.
And it all comes back to that basic question.
How do things work?
The question that drives all of science.
It's a question that never gets old.
So true.
And it's a question that will continue to lead us to incredible new discoveries.
This deep dive into the 2024 Nobel Prize in Physics has been a perfect example of that.
Definitely. It shows us that the search for knowledge, it doesn't have any limits.
Yeah.
And we can achieve amazing things when we go beyond what we think we know.
And embrace the unexpected.
Absolutely.
So until next time, everyone, keep those minds open and keep exploring.